Good evening to all of you and welcome. I think we'll go ahead and get started. If you, those who haven't found a seat yet could do that, that would be terrific. My name is Dorothy Harrell, and I am very honored to be the Chancellor of the University of Colorado, Denver. And this is my first Chancellor's Distinguished Lecture, so it gives me a great deal of pride to be here this evening. As many of you may know, that this lecture is made possible by the Damrauer Endowed Lectureship Fund. And it was created, this particular fund was created by Drs. Lenny and Bob Damrauer, who are cherished members of the CU Denver community. They established this in 2014 in honor of their parents, who did not have the opportunity themselves to attend college, but valued education greatly. So this lecture series is an opportunity for us to welcome all of you who are here tonight. I've met a number of faculty who are here. We have administrators, we have students who are here, and we have community members. And we have alumni faculty and alums of the university as well. So to all of you, we are so delighted that you've joined us tonight for something that is becoming a very special tradition in the life of the University of Colorado, Denver. This lectureship series, it's now in its third year, and it focuses on subjects that are of broad general interest and that appeal in science, technology, engineering, and mathematics, what we call the STEM disciplines. So let me tell you just a little bit more about Bob and Lenny. Bob has been with CU Denver since 1968. So he is one of our longtime esteemed colleagues, let me say that. One of the things I have learned about Bob during my time here is how much he cares about nurturing young faculty, and he's given me the opportunity to meet some of those along the way. And he has been certainly a guiding light in the chemistry department. So these days, he wears 3 hats, and that's no surprise when you know Bob, that he's a professor of chemistry, he's a special assistant to the provost, and within that chairs our review and for the promotion and tenure process, and he is also our associate vice chancellor for research. Lenny Damrauer was a longtime professor of chemistry before taking up a career in computer science. She worked in information systems at Children's Hospital here in Denver for more than 20 years. After she retired from the hospital, she returned to CU Denver and now works in our admissions office. Lenny and Bob really are very treasured members of the CU Denver family, and I know they have members of their family here tonight, their son and a couple of grandsons. So would all the Damrauers who are here please stand and let us acknowledge you. Bob. We are really grateful to you for establishing this fellowship. Thank you so very much. And it's my understanding that it, in the past, has yielded stimulating discussions and conversations. Past speakers have covered topics from ozone depletion to big data. And next year's speaker is already in place, and it will be Dr. Jennifer Doudna, who will speak on February 21st of 2018 about the complexities of gene regulation. And then in the fall of next year, 2018, we'll have Dr. George Church scheduled to speak about the human genome. So mark your calendars, because we hope you'll join us for those. It really is marvelous to learn about these kinds of topics, which ordinarily, I can tell you, are not the conversations over dinner at our house anyway. But these presentations and lectures present information in a way that is accessible to all of us. And as I was talking with our speaker for tonight, I said I'm really looking forward to that because I know that that's one aspect of this that will give us great information, but delivered in terminology and in the concepts that are very easy for us to understand. So I hope that you will continue to make this a pattern in coming to these events. So tonight, we are really fortunate to have with us a world-renowned speaker whose research is driving science into the future. Dr. Jennifer Lewis is one of the most foremost scholars in the area of biological engineering. She is a professor with the highly acclaimed Wyss Institute for Biologically Inspired Engineering. How about that? Biologically Inspired Engineering at Harvard University. She's a faculty member at Harvard University School of Engineering and Applied Science and has been there since 2013. She has taken 3D printing technologies to an entirely new level and manufactured printed electronics, soft robotics, and vascularized living tissues. Her lab is on the road to creating objects that sense and respond to the environment. Her work on microscale 3D printing was recently highlighted as one of the 10 breakthrough technologies by the MIT Technology Review. Her research has resulted in more than 30 patents and 150 papers. Dr. Lewis has won numerous awards, including the National Science Foundation Presidential Faculty Fellow Award. Prior to her work at Harvard University, Dr. Lewis was a professor and the director of the Materials Research Lab at the University of Illinois. I know she arrived yesterday and today has had the opportunity to meet with a number of our students and faculty, and for that we are really grateful as well. Her spouse, Dr. Lori Sanders, is with us here tonight. And Lori, will you stand up from where you are? And because Lori, Lori is the connection between CU Denver and Dr. Jennifer Lewis. Lori studied chemistry and here at CU Denver and was advised by Professor Bob Damrauer. So you're going to require me to call you Professor Bob. Anyway, how wonderful it is, because that's part of what I think is really spectacular about a place like CU Denver, that the faculty that we have here touch lives in ways that is never forgotten. And so, Lori, thank you very much for making this connection and making it possible for us to have Dr. Lewis with us tonight. So please join me in giving a very warm welcome to this year's speaker for the annual CU Denver Chancellor's Distinguished Lecture, Dr. Jennifer Lewis.
Thank you. Thank you so much. Thank you so much. Thank you. Wow. Well, let me begin by thanking the Chancellor for those very kind remarks. I really appreciate it. Hope I live up to it. I'd also like to thank the Damrauers, Lenny, Bob. I will say that from the very moment I met Lori, all I heard about was Bob Damrauer. He was like the best professor, and I'm like, one of our first trips together, we went up to Estes Park for a wedding, and I got to meet Bob and Lenny, and it's just been a privilege to really, now several years later, be here and have an opportunity to speak on campus. I spent the day on campus. I got to meet with a number of really bright and creative people who are changing the world, and from students and faculty to staff, InWorks, got to see maker spaces there, as well as in the library. So it's very exciting to be able to share some of the work that we're doing in my lab that started really at University of Illinois and has continued at Harvard. The title, 3D printing, making the future, is something I really believe in. I think we can use these kinds of digital tools to really rapidly innovate, design, and make. So if we think about 3D printing, I'm sure there's many of you in the audience that have heard this term, maybe all of you, because it's been in the popular media for the last 5-6 years, starting with an article, I think, in 2011 in The Economist, and it's just exploded. You can't listen to NPR or open the New York Times or whatever and not hear something about 3D printing. But the genesis of this field really started in the 1980s. So the first patents on 3D printing are, 35 years old now. And, the promise then was just this idea that you could take a digital design, a CAD file, a computer-aided design, and rapidly print it and make a three-dimensional object in a way that you didn't need expensive tooling. So you didn't need masks, you didn't need dyes, you didn't need a really costly mold, and that means that you could innovate quickly. A designer could have an idea and 24 hours later or less print a part, look at the design, change the part. We call these parts prototypes. And for about 3 decades, prototyping was really what 3D printing was good at. That was the sweet spot. It wasn't really used for anything besides helping the design and innovation cycle. But in the last few years, there's been another revolution, and it's really now being explored and widely used for manufacturing. I've got several examples here, and I'll talk about those parts, but I think also there's a revolution in the academic community because now we're being able to create things that maybe can't be made by any other way. And I'll give a highlight of that as well. And hopefully you'll see in some of the research that we're doing that that's very true. So, this part, sort of design to part is one aspect. The idea for being able to have unprecedented control over composition, over structure, and then to unlock new performance properties. So I'll start with this middle image. This is really an academic kind of research. This appeared in Science a few years ago. It was done at Caltech and JPL, or HRL, I should say, Hughes Research Lab. And what you're looking at here is a metallic lattice. And this is a component of that lattice under higher magnification. It's metal, it has thin walls, 100 nanometers thick. Just to give you a sense, the width of a human hair is 0.1 millimeters. So this is many orders of magnitude thinner. And it was printed by first printing a polymer structure, coating that structure with metal, eliminating the polymer to leave hollow channels behind. It's 1,000 times less dense than water, and water's pretty low density. And so you can see it sitting on top of this dandelion. It can support it easily without, crushing, if you will, because it's so light. And this has remarkable mechanical properties, exceptional stiffness, and very high resilience. So these other parts that I'm showing here are really examples of this manufacturing revolution that I was talking about. This is an example of a fuel injector nozzle. It was printed in a single pass, so the entire design made by conventional means required 18 different parts assembled together. So this is a simplified part that can be printed in one go. It has a lot of internal structure because it's a fuel injector, so you're mixing components together. And this is now being used in GE Aviation, so in aerospace applications. And GE is really buying into digital manufacturing. They recently spent over $1 billion to buy 2 metal manufacturing companies, 3D printing metal manufacturing companies, in order to really unlock this for digital manufacturing. So one thing is complex shapes. Another is the fact that you can make things that you can't make by any other way. And finally, this idea of mass customization. The idea that if we're going to print parts to a human form, it's not going to be economically feasible to have a mold for every human, sort of orthodontics or hearing aid shell. If we can print this, we can do this at a very low cost. And so these are 2 examples of things that are being, commercialized right now. 98% of all in-the-ear hearing aid molds are 3D printed, but the electronics are hand-potted, and it takes a week. And by the way, hearing aids are about 30 times more expensive per ounce than gold. And if we could 3D print the entire thing, including the electronics, that would really drive innovation even more. So let's look at the types of printers that exist in the ecosystem. Some of you here have probably used desktop versions, MakerBots, Formlabs. This is a commercial large-scale printer. These two here are on the order of a few $1,000s a printer. This one is about $1.5 million for one printer. What's the difference? Well, here we're using a very high-powered laser to locally melt powder together, and I'll describe that in a little bit more detail on the next slide. Here we're using light to UV cure polymer resins. And here we're using a hot glue gun, essentially, to melt a plastic material, print it out onto something that cools very quickly and solidifies. But if we look across this, no matter if it's a low-cost printer or a very expensive printer, there's really been three basic materials that have been used: powders, polymer powders or metal powders, UV curable resins, and thermoplastic filaments. And as a material scientist, we're really driving this idea of how can we bring more materials into the ecosystem and unlock more power of 3D printing. So parts printed by particle fusion, you use a very high-powered laser, you locally melt the particles, they re-solidify, and you can build things that are very complex, like this turbocharged rotor. This is a cutaway of this. Here you can see where the laser is impinging and solidifying, and down below you can see all of the subsequent layers that have been previously printed before you get to this layer. So the process goes like this: spread a layer of powder, use a high-powered laser to locally melt where you want the part to be printed, spread another layer of powder, use the laser, and so forth and so on, and build up. These are the in-the-ear hearing aid molds done in a liquid resin. These are support structures that have to be removed from the shell before you use it. And this is just a printed part out of an FDM head where you're feeding in thermoplastic filament. And in order here, you have to have a support material. Here, the liquid resin, and these features are support material. Here, the powder bed is a support material. You always have to remove that support material. That's kind of cumbersome. So we've developed a printing process where you need no support material, and I'll describe that in more detail. So even though this field is 3.5 decades old, if you look at a report that came out a few years ago, the idea is that it's still in its infancy, and it's really only the tip of the iceberg that's really been explored so far for 3D printing. Prototyping being one of them, plastic aircraft parts. Now we're starting to see metal aircraft parts like the fuel injector that I showed. So just in a few years' time, the water is receding, and we're unlocking more and more of these potential applications, right? We're down here. So this is what my lab is trying to do. We're trying to bring in electronics, batteries, living tissues, autonomous structures. And I'm going to try to quickly run through some examples of the work that we've been doing over the last few years. Everything that I'm going to present today is within the last 2 to 3 years of research. And to do this, we're bringing in new materials, and we're also bringing in the capability of printing multiple materials at one time that actually add function. So how do we do that? Well, it's a pretty simple process, to be really honest. We're taking a syringe and we're filling it with material. The material's kind of the secret sauce. That's what we do. We're material scientists. But we have a printer that has the ability to come in with 4 different heads and print different materials. So if we're making a flexible electronic, we might, as I'll show you, we might have one material that's a soft elastomeric structure. We might have one material that's a conductive ink. We might use one head as a pick and place tool. If we're making a battery, we might have an anode and a cathode being printed. If we're making human tissue, cells, we need something that's going to form a vasculature to keep the cells alive. We need extracellular matrix. We need all of these things together. So we're printing these filaments, and as you can see, we're doing it without support. Those filaments are self-supporting. They're spanning gaps in the underlying layers. We don't need anything to keep that ink from spanning or deflecting. How do we do that? Well, that's one of the aspects that we call rheology, tailoring the flow, and I'll describe that in more detail. We're doing all of this at room temperature, and as I said, we have the ability to integrate many materials in a single build sequence. So this is one of the sort of more sciencey slides with a couple of equations. I won't spend a lot of time on it, except to say that every one of you has used a material that has the rheology that our inks have. At least I hope so. Because today, I hope every one of you brushed your teeth. Okay? I did at least twice. So what is toothpaste? Well, if you squeeze a tube of toothpaste, you get a filament that comes out. And you want it to keep its filamentary shape when it sits on your bristle, the bristles of your brush. That's the kind of rheology we're putting into our inks, just like that. A little more sophisticated in terms of their function, but if you look at it, what happens when you squeeze a tube of toothpaste? As you squeeze it, it's easier to make the ink flow. That's called shear thinning. So that's a term that we'll hear me say many times. As you squeeze harder and harder, it flows more easily. That's shear thinning. The other interesting feature of our inks is just like the toothpaste, when it comes out, you don't want it to keep flowing and run off your brush, right? So we want to have what's called viscoelasticity. We want the viscous part so it flows, and we want the elastic part so it solidifies the minute the ink comes out of the nozzle. And if it solidifies at room temperature, it's not because of a temperature change, it's because we've engineered some structure into the ink that allows it to be solid-like. And because it's solid-like, it can span gaps without deformation. And it doesn't need a support. So that's the key thing. So keep this in mind for the rest of the talk. Okay, so I may have been a bit too ambitious in the number of examples I'm going to give. And so if we get to a point where either I see complete fatigue or time is running out, we may skip one or two topics at the end. But what I'm going to try to show is just some highlights from our group where we really are bringing new materials to 3D printing. And because of that, we're able to create some things that really can't be created on commercial printers. So one of the things we're creating are soft electronics, micro batteries the size of a single grain of sand. Probably pretty hard to make otherwise. A soft robot, which has gotten a tremendous amount of attention for something that I believe is, well, you'll see. I'll keep you guessing for just a little bit. And it's probably because this image was, image is everything, and Laurie Sanders took this image, and she's a scientific photographer, so she's probably responsible for all the publicity we've gotten on that work. And then the vascularized tissues, which I think, captures a lot of people's imagination. So let's start with electronics. All of us have cell phones. If we were able to open up the cell phone, what you would see is a printed circuit board. It's rigid, right? It has rigid components on basically a glass fiber reinforced board, very stiff. Well, we're really interested in soft conformal electronics, and we're interested in ones that we can print. And so this is a component that I'll describe in more detail, but it has a soft matrix. We're using some of the same standard components here. We're picking and placing and adding them to this device, but because the matrix is now soft, it can wrap around. It can be textile mounted. And as I'll show you, this can be used in the sensing scheme. All right, so let's take a look at another graph with data, but start here. This is our silver ink on this background material. This LED is getting dimmer and dimmer. Keep going. A little bit more dim. Oh my gosh, it's gonna turn off. All right, and there you go. Now, we've stretched this so much that we've basically broken the electrical conducting features in here, which are silver particles. Once this comes back to its original state, the resistance goes back down, the electrical conductivity goes way up, the brightness comes up. The important thing is that these electrodes can be stretched many times, their initial strain up to about 200%, and still provide electrical contact. So these are highly flexible, highly stretchable materials. And that is important for conformal electronics. So if we want to build, of course I'm at Harvard, got to build the Harvard H. We want to build something like, you got to do it. So here's an H that we built. I'll show you how we build it. Each one of these is an LED. You can see the sort of highlight of the conductive inks that are being written. And it's, on top of that, we're using our printer in reverse. We're using a nozzle that has no ink in it. Instead of pressurizing and flowing ink through it, we're pulling a light vacuum. We're doing it in reverse, and we're just being able to pick up the component, drop it down. All right, so let's see how it works. So we call this hybrid 3D printing because it's a combination of printing plus auto pick and place. And if you think about that printed circuit board or any circuit board that you have in your computer, in your phone, you have a pick and place tool that's also picking and placing all of those devices, resistors, LEDs, and so forth. So we put down some magnetic connectors that we're going to use to wire up to a power supply. You see now we're connecting the final traces between the printed silver ink and our LEDs. You can pull it up off the printer, and voila, very flexible, right? That's the H that I just showed you in the LED. All right, so let's do something a little more practical. Let's make a strain sensor. I just showed you in that LED demonstration, as I stretch this material, the resistance goes up. So if I have a strain sensor here, and I mount that, let's say on a joint, and you start to bend your elbow, that distance is going to increase. And if I have an Arduino chip and I program it so that these LEDs start to light up, 1, 2, 3, 4, 5, more strain, more LEDs light up, then it gets kind of interesting. So we printed this, we printed this, we printed them together. And this is one of my students, John Ahrens, and you can start to see the LEDs lighting up. The more he bends his elbow, and then as he starts to come back, they go away, right? So imagine you had an injury and you wanted to do rehab and you wanted to be able to monitor your flexibility and how much your motion, how much your mobility was recovering over time. Really low cost, really easy, simple textile mounted devices. So that's conformal electronics. That's the first story. Okay, so we got interested in batteries as well. As I was telling you about hearing aids, if we want to be able to print a whole hearing aid, not just the plastic shell, we need to be able to print conductive features. We need to be able to pick and place. Maybe we want to make a battery that's actually to the shape of the hearing aid rather than trying to make the hearing aid or whatever device around the shape of the battery. So this is, a Kilobot, which is coming out of a lab at Harvard, these tiny little swarm robots. And you can see that the entire design for this robot was built around a coin cell battery that's sitting here. And all of the electronics were packaged, and there's a green printed circuit board. This is not my work, by the way. This is Radhika Nagpal's work. Brilliant, brilliant person. But if we look at the current types of lithium-ion rechargeable batteries that you can buy commercially, they come in about, well, actually 4 flavors, but I'm showing 3. Coin cells, pouch cells, which are in your iPhones, and cylindrical cells, which are actually, many of those are used to power electric vehicles. So they're arrayed in such a way that if you were actually to open up the bottom of a Tesla and look at the battery packs, it would just be a ton of these cylindrical cells, all arrayed and connected together. They're rechargeable, of course, and that's good. All of these are layered architectures, and they have layers that provide a function. So let's do a little bit of a dive on how batteries work. So all of us rely on our batteries. We're addicted to our cell phones. We use our computers all the time. A lithium-ion battery works by having an anode and a cathode connected to current collectors. And it's called a lithium-ion battery because the lithium is playing a really important role. When you're charging and discharging, lithium ions are moving from the anode to the cathode and back again when you discharge. So this idea of having the ability to print materials that are lithium-based is important if we want to try to make a battery. Okay. So we got excited about white space. In my lab, it's always about white space. What can we do that nobody else can do? And if we're going to do something in batteries and we look at all these different cells that are available commercially, well, wow, there's a lot of real estate down here, white space, right? That, if you think about it, this is a millimeter cubed of volume. Tiny, single grain of sand. Think single grain of sand. And why might we want to print a single grain of sand battery, a battery the size of a single grain of sand? Well, this is a great image. It's from a colleague at UC Berkeley, Chris Pfister's group. He developed this, coined the term smart dust. Internet of Things, think of that, a sensor. Well, look at, when I think of dust, I think of things that are kind of in the air, right? And that settle down and sense. You're not gonna be able to, fly that very far if it's tethered to a coin cell battery. That's just gonna weigh it down, right? So we've got a device here. Wow, why can't we print a battery maybe that's, can power this device but not be so bulky? So that was really our goal. The way we did it is we made two inks, very pasty-like inks, toothpastey-like inks. One is called an LTO anode, lithium titanate oxide. This one is LFP, lithium iron phosphate. And this material is the cathode, and this material is the anode. We have first deposited gold contacts on glass. These are interdigitated electrodes. These are the current collectors. On each of these interdigitated teeth, we're printing an anode and then the cathode. And then you'll see we package that battery. We encase this in this first generation design of plastic case. It's filled with liquid electrolyte through which the lithium ions and the electrons move. So this is just an example of us printing one of the anode architectures. Again, because it's a filamentary process, we can build something where if you look down at this wall, it's very narrow. It's a 30 micron nozzle. Again, a third of the width of the human hair. We're building up layer by layer so we can create batteries that have a very high aspect ratio walls, and then a width that remains whatever the print nozzle that is being used. As we add layers, we add height, but we don't make it wider. Once we've printed all of these little anodes, we can come in and interdigitate the cathode inside these teeth. Just to give you a size scale, that's our little battery right there. It really is very small. Okay. Now, having said that, it doesn't have a lot of energy density or energy capacity, right? Because it's really small. But it works. So we then interdigitate. So the white is the anode, the dark features as the lithium iron phosphate. That's interdigitated. And if we just do a charge-discharge number of cycles, this is 25 cycles of charge-discharge, we can measure the energy capacity per area. For micro batteries, area is really the name of the game. They're normally made by thin film deposition. Now we're able to go out of plane, obviously, through a number of layers. And this is what the battery performance looks like, charge-discharge. Pretty stable, it works. Then we packaged it. Well, generation one pretty much was a disaster. But, we're makers, so we used a CNC mill to package this battery. There's the little battery sitting in here. The package is, many, many times the size of the battery. Plus you have these gold contacts. And by the time you're done, your little micro battery is like, the size that's much larger than a grain of sand. So I have a very talented PhD student, Tensing Wei, and he was committed to making a fully 3D printed battery. And I was like, yeah, let's do it. So let's print everything. Let's print the separator. Let's print the packaging material. Let's print the anode and the cathode. And this is now our latest generation battery. It's much bigger because we do want to power something kind of useful. Here it is sitting out of the glove box. It works. The entire thing is 3D printed, many, many layers. And yeah, so that's the battery story. All right, we're going to move on to soft robots. Soft robots, big deal at Harvard because George Whiteside's group, for those of you who know him, very well known in chemistry, really an intellectual leader in many, many areas. He published a paper several years ago that got a tremendous amount of press. And here's our little robot walking across. See all this tethered stuff? That is what's being used to actuate by air a pneumatic network that's embedded in elastomer. So that's a fancy word for silicone bathroom caulking material. Right? Just to make sure we all know what we're talking about. So rubbery, elastomer, silicone, that's what we mean by that. And then this is Rob Wood's group. He made this sort of origami-like robot that is powered by 2 battery packs that kind of self-folds and walks away. So both of these are tethered. We're tethered to, even though this is a soft robot, it's tethered to a rigid power supply. This is soft material tethered to rigid batteries. And so the question is, could we make a fully autonomous, fully soft robot? And we worked with both George and Rob Wood to accomplish this. And this is that figure this image I was telling you about. Very, very proud of Lori's work here. Received NSF top 10 for best photography in science, and recently in this competition is called the Visi Challenge. But you can see there's a lot going on inside this piece of silicone bathroom caulk, right? And it's pretty complicated. So what's going on? What's all this stuff, right? I mean, we've got these little features here. We've got something going on here. So I want to walk you through how we made this and what are the key design components. By the way, we call this the Octobot, you know? Okay. A little bit looks like an octopus. And actually, some of the original soft robots were sort of inspired by an octopus because, you know, they can go into like a Coke bottle and out. Like they can morph and squeeze and change their shape and all kinds of things. So let me go back real quick so I can come back into this slide. All right, so first things we had to do was get rid of the hard. So I've been telling you in the first part of the talk, you know, we can do electronics, we can do batteries, and now I'm going to say, wow, we don't want that. So the first thing we need is a liquid fuel. A liquid fuel, we need the air to actuate the body of the robot. So we use hydrogen peroxide. When it comes into contact with platinum particles, you can see a big amount of gases formed. This is a thermal image. High temperature occurs. That's our power supply. So just like you go to the gas station, you fill up your car with gas, and you know that powers your car. This is what's going to power our little Octobot. The next thing we did was we needed to be able to, you know, control when that fuel was injected into the robot arms. And we did that using microfluidics. And hopefully this movie is going to play. Yeah, I think it's playing. No? There we go. So this is just an oscillator. It's shifting from one side to the other. It's allowing fluid that would be delivered to hit a catalyst to shift between two states, on, off, on, off. And it's all done, again, in PDMS, bathroom caulk. And, but it's a pretty sophisticated circuit, right? We can think about this as a fluidic circuit rather than an electronic circuit. So we don't want to put all this together. We need to be able to seamlessly integrate pneumatic networks to carry that air, the gas that's formed, to power. We need an onboard fuel reservoir sitting here in the back of the Octobot's body. We need catalytic features that are going to drive that liquid to gas transition, that reaction. And we need that controller that's going to allow us to turn on and off so that, you know, we can have these opposing arms of the octopus move. Okay, so that's what we need to do. How are we going to make something that looks like this at the end of the day? We need many materials. We develop a fugitive ink that we can print that then opens up and leaves the body and opens up channels. So we call it a fugitive ink because we're printing the network, but then it goes away, leaving open air passages. We need a catalytic ink so that after the hydrogen peroxide comes out of the fluidic logic, it hits this, forms gas, and then inflates the arms. And we need the reservoir back here. We need a body. We need these arms that are soft and extensible so they can move when this reaction takes place. Okay, again, I won't go into all the details about these inks, but we made these inks and they have the rheology that we want, and you know, we can put particles in there that are platinum laden so that we can have the catalyst. We have this fugitive material that will go away. I'll come back because that fugitive material plays a role in our vascularized tissues too. So embedded 3D printing is how we're going to do this. And this is what embedded 3D printing is. We're coming down into a reservoir. Think about printing inside Jell-O. And we're writing a pattern. And this is a vascular, three-dimensional vascular network. It's going to be open channels. And you can see that we can go down inside this glass and we can print whatever we want, right? So that's how we're going to make our Octobot. Okay, so here's the mold. We've filled the Octobot. Now we're taking a nozzle, we're going down in, and all we're using 3D printing to do in this case is the functional parts. The catalytic features, the depot for the fuel, and the pneumatic networks along each arm that are going to be able to be, pressurized and allow for the arms to move. So we had to print a catalytic ink, we had to print the fugitive ink, and we had to print regions here where we could connect to the microfluidic chip that we put down inside the mold. So we start with an empty mold, we put the chip, the microfluidic chip inside the mold, we top it off with a little bit of elastomer, we fill it with then the EcoFlex, which is more extensible, then we come down and we print the function. The catalytic features, the features that are going to be open channels. There we go. So this is the same Octobot picture. Now, rather than showing you the materials, I'm showing you what each of these regions are. The reaction chamber, the actuators, the soft controller, which is sitting here, and so forth. And this is a schematic view of the Octobot in a very simple way, where we have these arms, which are going to be actuated. And each one of these arms, when we inflate, there's an expansion event, and they rise up. They basically bend, and we can, because of the fluidic network, we can switch between opposing arms. So 4 will go at one, then we'll switch to red. The other 4, the opposite 4, will go switching between using that microfluidic oscillating element that I showed you earlier. And let's see how it works. There we go. So remember, we want to get rid of the tether. So this movie should be playing. I don't know if it is. Let me see. Here we go. The tethers are gone now, and the onboard fuel is here, and you can kind of see the arms are oscillating. We also have a vent, because once we pressurize, we got to depressurize. And so this is the Octobot. It is really, truly the first fully soft robot. At the same time, all it does is twitch. So I mean, there's a long way to go, right? It's not walking, it's twitching, people, it's twitching. But, okay, we're in nature, I don't know. Sometimes, things that you kind of don't think are gonna end up in nature, but I'm not gonna say anything about that. So we're just gonna be grateful. All right, last topic. All right, so when I moved to Harvard 4 years ago, we really wanted to start printing tissues because, as I showed you, we can print vasculature. We can print open channels inside things. And for the last 20 plus years, the thing that's really been holding back tissue engineering, or at least one major limitation, has been the idea that if you try to print a three-dimensional tissue, if you get beyond about 500 microns or a half a millimeter thick, cells in the center of the tissue start to die. They have to be within a few hundred microns in your body, for example, have to be within a few hundred microns of a vascular supply to get nutrients, oxygen, to get rid of waste products. So you can print a lot of cells, but unless you can put down vasculature too, you can't print true three-dimensional tissues. So we already figured out a way to print vasculature, right? But we had no idea about how to print cells. So we did our best, and I'll show you some examples of that. Why do we care about human tissues? Well, there's a number of things where human tissues can really be important. If we think about the pharmaceutical industry, it's a pretty good amount of money spent every year trying to bring drugs to the market. And many of them fail in clinical trials. Prior to going into humans, prior to doing clinical trials, phase 1, phase 2, phase 3, They're tested in a dish, 2D cell culture on human cells, and they're tested in animals. Animals don't always really recapitulate our biology, right? So what if we could really test these on three-dimensional structures that are human tissue and have a very quick phase 0 trial to prevent all of this extra money that's being spent down the pipeline once you get to clinical trials? That's sort of the first driver. The second driver is the fact that, you know, the grand challenge truly is to try to create tissues for repair and regeneration. The organ donor list, there's about 120,000 people on the organ donor list in the US right now. 100,000 of them are waiting for kidneys. Many of them are on dialysis. Dialysis is a disease in and of itself. Once you go on dialysis, you literally have about 5 years. If you do not get a kidney, by the time 5 years ends, you're not going to make it. I mean, you're just not going to make it. So 100,000 people are waiting for organs. This is a relatively flat amount of, you know, people that are donating. This is going up, and it's just going to keep becoming ever more problematic. So that's the big driver. That's what motivates us. That's what gets us up every day, my students, my postdocs, myself. But tissues are pretty complex. So if you really want to think about tissues, there's many tissue types. There's hundreds of different cells in the body. We talked about the fact that there's vasculature, there are properties, there are mechanical properties span many orders of magnitude. It's not simple to recapitulate human tissue in a way that really speaks to the kinds of organs that are needed, like kidneys. So I already made the point that we need vasculature to be incorporated or cells will die. These are real, you know, this is a real image of a liver vascular structure. You'll see big channels and then many, many small capillaries. Our thesis is we want to provide the highways, which are the big channels, and we want biology to do the rest, to create the capillaries. This is a process known as angiogenesis or tubulogenesis. So I'm going to show you, you know, just the ability to print big channels, like hundreds of microns, as opposed to capillaries. But it's a step. It's a step in the right direction. So how do we do that? We use multi-material bioprinting. We load these individual ink reservoirs with cells of interest, with extracellular matrix. What that means is hydrogels. Again, think Jell-O, right? It's not a bad analogy. In fact, one of our inks contains gelatin, the key ingredient in Jell-O. And if you think about your extracellular matrix, it has these kinds of proteins and a lot of water. That's what an extracellular matrix does. It encapsulates cells. It provides some structural support. So we need to be able to print extracellular matrix, we need to print cells, and we need to print that fugitive ink that I described earlier to create those open channels. We bring all that together, we can create a tissue. So let me say a little bit more about our extracellular matrix. It's a combination of fibrin and it's a combination of gelatin. And I won't go into all of the details here, but these are a number of different cell types of interest. Fibroblast cells, which are in your connective tissue, endothelial cells, which line your blood vessels, very important, and, you know, different types of smooth muscle cells, stem cells in this case, human mesenchymal stem cells. All of these play very nicely with our extracellular matrix that we've engineered. Here's our fugitive ink. In this case, we're going to cool the sample after we've printed it. And this material, which is viscoelastic and gel-like at room temperature, liquefies as we cool it down to below room temperature. And that's not something you normally think of. Normally, when you think about melting something, you heat it up, right? This is an interesting chemistry issue. I won't go into all the details, but there's hydrophobic interactions that make it gel-like at room temperature, but when you cool it down, it liquefies. So we can basically suck it out of the channels where we printed it. So let's look at a very simple tissue construct to begin with. So the first thing we're doing is just printing a PDMS border. That's not the tissue. That is one of our vascular features in the tissue. That is our fugitive ink that we've just printed. Everywhere you see clear ink, There, you're going to open that up, remove it, and leave behind an open channel. Above and below it, we're just printing two different fibroblast-laden inks. So these are the connective tissue, the cells in your connective tissue. You see that ink looks kind of chunky. That has to do with the fact that it has gelatin in there, and we're going to keep printing. It's a very simple 4-layer architecture, not too complicated for Gen 1. And because we've labeled these cells with different fluorophores, when we look at it under a fluorescence microscope, we can see red cells, which correspond to the vascular endothelial cells, and two different types of fibroblast cells. Now, ultimately, after we've printed this small feature, we're filling all of this in with our extracellular matrix. We're taking it down to 4 degrees C. We're just, in this first generation, we're just coming in with these two syringes, and we're pulling up, and we open up those channels. So now we have open channels in our 3-dimensional tissue through which we can flow nutrients. But first, we're going to line those channels with endothelial cells. So we're going to first introduce endothelial cells. This is a live dead stain. So even though these cells in the next figure will look red under fluorescence protein, we didn't use the fluorescence version of them, but in a live dead stain, they're alive. Most of the cells are alive. You see very few red cells. So we can print these, the cells live, we can seed the open channels, we can line those in a confluent manner. This is very early on after seeding. They haven't grown to confluency. And this is what the tissue looks like. Well, again, 4 layers, not that exciting. We just got some fibroblast cells, not that functional. So the next thing we did was to try to create something where we can create a tissue that might be of more interest. So this was using a stem cell line that you can differentiate to bone. Okay, so now we're going to try to create a much thicker construct. We're going to use those channels. We're going to perfuse those chips, those tissue chips. This is the construct that we've built. This is a cutaway of this tissue after we've essentially fed it with growth factors that are going to drive differentiation to form bone mineral. So if we look inside these chips, this is just, again, a very simple construct. This is what the 2 vascular channels look like. Here are the channels. The green cells are fibroblasts. Mind you, all of these cells are being kept alive for many, many days. They stay alive. We're feeding them. We're giving them nutrients. We're taking away waste products in a perfusible manner. This is what one of those channels looks like in confocal. You can see the individual endothelial cells lining. This is a bit more biology than you probably need to know, but these cells form very tight junctions, just like they would in your human blood vessels. All right, so let's make a thick tissue. I won't go into all the details here, but we're going to try to create now a tissue that's about 1 centimeter thick. Definitely without vasculature, those cells would die. So layer 1 is our fugitive ink. We start to print our stem cell laden ink. Now, we can also print out of plane. So we're printing these posts that are going to connect the bottom layer to the top layer, which is our vasculature. So now we have a 3-dimensional vasculature that's interpenetrating this thick tissue sample. And if we go to the next slide, you can see all of this pink stuff is going to be the open channels. All of this sort of clear, chunky ink is the stem cell laden material. And then we fill around all these open regions with extracellular matrix. So at the end of the day, we pour extracellular matrix and fill in this entire tissue. And then we start feeding it chemicals. And I didn't go into all the details about the cocktail that we feed, but basically it drives the stem cells to differentiate and to create and lay down bone mineral, calcium phosphate. And you can see here, osteocalcin is stained in purple. A lot of bone minerals being deposited. This is after 30 days. In addition to bone mineral, collagen 1, which was not in our extracellular matrix, which the cells are laying down themselves, part of your extracellular matrix, the cells are doing things. They're not just sitting there. They're making minerals, they're laying down their own extracellular matrix, and we can capture all of this. And we can watch this in real time, and we can see how this tissue is evolving. And if without vasculature, it's dead. With vasculature, you can see a lot of mineralization has been laid down. These cells are very active. They're creating they're creating bone, basically. All right, I think we're getting to that fatigue point, I can tell. Quickly, if we can line channels with endothelial cells to create blood vessels, we can line them with epithelial cells to create kidney tubules. Okay, we can do that, and we have. And I won't go into all the details, but if we look at a kidney, it has these filtration units. There's 1 million of them. They filter your blood. They take out the toxins. And once that's happened here in the glomerulus, they go through this thing called the proximal tubule, which we're going to print. And the proximal tubule says, hey, let's put some of the good stuff back in the blood. So that's important, right? It's like cleaning your bedroom. If you do it the way your kidney does it, you take everything out of your bedroom. Your dresser, your bed, and then, of course, the mess that you've made, right? But you got to go to sleep, right? So you got to bring the bed back in, and you got to bring the dresser back in. Well, that's what your kidney does. It takes everything out of your blood, and then it says, oh, we better put the good stuff back in. The good stuff back in goes right here in this proximal tubule. Okay, so we can print it. This is the open channel. We've opened it with our fugitive ink. Then we can fill in these cells. Yep, there comes the proximal tubule epithelial cells. That's day 1. Day 0, well, day -1 is when we made the open channels. Day 0, we fill the cells. Takes these a long time to actually mature. 3 weeks later, they form a confluent lining. I think I'm going to pass by some of this, but look, it's beautiful. The cells are all tightly packed together. They're doing their thing. A lot of details, don't need to know it, but they're functioning. Their structure looks a lot like the cells that you would find in the body. They have, these little primary cilia. They have microvilli. They have everything. And they're much better looking than they would be if they were on a dish. Like the 3D environment really matters. I won't show you all the details, but it matters. We can use this to study drug toxicity. So the last thing I'll show you is cyclosporin A is a immunosuppressant. If you do get a kidney transplant, you get this drug to help allow you not to reject the organ from the donor. It turns out that it's also a known nephrotoxin. So this is at very high dosages, of course, but look what happens. It starts to perforate that cell lining. That's not good, right? And this is just a movie that shows what happens. So you can use these models even before you do implantation, and we're a long way from that, but you can use these to study the effects of drugs. And 20% of all drugs fail in phase 3, which is the last trial. You've already spent a ton of money to get there due to nephrotoxicity. So 1 in 5 drugs at the end of phase 3 don't go to the market because of nephrotoxicity. So we can use this as a platform. We're working with Roche Pharmaceuticals. They're super excited about this model. The question I know you're going to ask is, when are we going to print organs? The question I'm going to answer is, I'm not sure. But I get inspired by coming back full circle to electronics. I get inspired by this plot. This is known as Moore's Law. The first transistor, Bell Labs. This is not a solid-state transistor. The first solid-state transistor was like early 70s, 1. 20 years later, it was 1 million. Now we're in the billions, right? A kidney has 1 million nephrons. We've printed a part of one of the nephrons. We're probably still at T equals minus something here. So if you scale it by Moore's Law, it's maybe 20 plus years away, right? Nobody wants to hear that. They want it like now, and of course I would love it to be now too. But realistically, we're talking about it's a long road still. So I'll end with, hey, I hope you enjoyed this lecture. I didn't talk about all of our work, but I tried to highlight some. And if you could print anything, what would you make? I want to thank all these people. I didn't do this work. These guys did the work. They're the rock stars. My students, my postdocs, undergrads that work in the lab, they're the people that make this happen. So thank you so much. I'm happy to answer any questions you have. Thanks so much. One question that somebody has that you'd like to ask, Jennifer. One burning
And if I could just ask that if you have a question, raise your hand. I'll bring you the microphone. Since we are recording the lecture, we would like to hear your questions.
Fatigue has set in.
Thank you very much for a very good presentation. Really inspiring.
Thank you.
My question is, I was looking at the scale of your work. Do you do this 3D printing under a microscope?
No. So our minimum features that we can print, it depends on the ink, but the smallest is a micron. We have printers that have very high resolution. Much of what I showed today was, minimum feature size of 30 microns for the battery, up to say 100 to 200 micron minimum feature size for tissues and things like that. But depending on the ink designs, we can really, literally go down to a micron in the smallest features that we use. But these are our printers. Some of them can print a meter squared of area, meter squared, right? So we don't use a microscope to do the printing, but sometimes we have a telescopic lens that allows us to visualize the printing as it's happening. So the battery work, we use a telescopic lens to see that to see those little battery electrodes. Everything else was just done with a regular video camera. That's a good question. Thanks for asking that. Okay.
Hello, thank you for your presentation. I have a question regarding the bioethics of the development of this, the tissue and the end product. And there's a whole school of thought that surrounds that, both pro and con. Can you address that for a moment, if you would?
I mean, I'm not an ethicist, so I can tell you that I think it is something that needs to be looked at. I think, what's going to happen, I think in this case, we're using, you can imagine replacing the stem cells that I show with patient-specific stem cells. So it's coming from the person that it's going back into. That's one thing to think about. There are, and if, there's been an advertisement for Jennifer Doudna, I mean, CRISPR-Cas9, I think, opens up like a whole nother level of biohacking, right? Of being able to turn on and off genes. I think there is a lot to consider there, and we're not at a point yet, I think, that we have to, at least in my work, really wrestle with that, but I hope we get to a point where we do, because that means we're making real possible translation into the clinic. So I hope we have that problem. I'm not an expert. Yeah, it's a good question, though. Okay. Bob? Uh-oh.
Is this open?
Yeah.
I don't have a question.
Okay.
Is this open?
Yeah, I think so.
Yeah. So, George Whitesides. I walked into my first graduate school class, and George Whitesides was the professor.
Wow.
He was like a year, maybe older, but I think younger than all of the students in the class.
I believe it.
And, the rest of us are here and other places, but George is at Harvard.
Yeah.
Along with her.
George is a really amazing person. So, small world. And thank you. I don't know if you want to say anything else, but thank you so much.
Well, we just wanted to thank you, Jennifer. What a fascinating lecture. And I can only imagine what we will all be intrigued to see what comes next. And to know that we had a chance to hear about it at this stage is really thrilling. So thank you very much, Lori. Thanks so much for making this connection. Thanks to the Dan Rowers and for making this possible. And thanks to all of you for being here tonight. So.